Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in the last session, we are discussing the spacecraft in connection with spacecraft charging. We discussed what are the different plasma fluxes that affects the spacecraft charging, namely the primary fluxes, primary electron and ion fluxes, then the secondary electrons due to primary ion or electron, then the backscattered electrons as well as the photoelectric emission. So, these are the things we discussed. Then we discussed that considering different current components, a valence equation using the Kirchhoff's current law. What is the Kirchhoff's current law? That is, whatever the ingoing currents has to be equal to the outgoing currents. Of course, during the time of the charging, when the spacecraft potential is developed, then the Kirchhoff's current law is not valid and there will be some net current there. So, we will be continuing with the same topic. So, once I get the current, or then I can use the lumped circuit model and we can show that how the spacecraft gets charged, what is the transient, what is the temporal behavior of the potential and what is the time it takes to get build up to get to reach to an equilibrium value. So, this thing we can do it by finding the equivalent circuit model of the spacecraft. Today, we will discuss that. And then whatever we are discussing from the very beginning, we are considering the charges that are accumulated on the surface, but we will see that there are not only the surface, the charges will be there on the surface, they can enter inside the spacecraft also, that also we will be discussing today. And then we will be discussing what are the effects of that spacecraft charging. So, these are the topics today we are going to cover. We just left yesterday with this equation. So, this is the equation where all the current components are there. So, these are all the it is all those components we are considering as the incoming or the outgoing and the incoming. So, considering that all these current components, we are writing this equation and you see here I have not written that equal to 0. So, when this will become 0, when all the incoming and the outgoing currents the balances each other, only that time the I net will be 0, but during the charging there will be a net current. So, whatever the formula and all those the modeling we have given, the plasma modeling, that is from the plasma fluxes, when you calculate all the currents. So, during the charging period I can compute what is my I net, and when I know this, I gave you this formula for the J net. So, when I know this whatever the different the components of this one J I, then J E, all those components, then I can compute the total current. So, this will be J net. J net means I am considering the flux density or the current density. Then when I multiply it by the area of the spacecraft, so I get the total current. So, once I get that, so I can this I can write, that is I can write in terms of the charge. So, charge and the potential are related. So, Q, if it is the charge, then that is related to C into B. So, I net I can write it is, so I can differentiate both the sides. So, dq by dt will be equal to, so I should write it phi here, phi s. So, it is basically it is at time t. So, dq by dt will be C d phi s t by dt, and this is equal to the I net. So, this is I net. So, I net is equal to C into d phi s t by dt, and then you can find you can get this equation. okay, where A is the area of the total surface of the spacecraft body. So, this is this whatever I was showing you, whenever we are needed to do a spacecraft charging analysis, to evaluate the equivalent circuit parameters, especially the capacitance, it is needed to be done. And the spacecraft consists of different types of materials. It can be an insulating material, it can be a conducting material, there can be semiconductors, there are different types of the material. So, while computing the capacitance, you need to take the material properties as well as the geometry also. Okay. Now, let us see how we do that. So, the equivalent electrical circuit model of the spacecraft, it is developed, or I will tell you in brief what is the method to predict the surface charging, and it relies on the use of the current input terms applied independently to the surfaces. Means whatever the current components, some 6 or 7 current components we considered. So, all those current components you take into consideration, and then you assume that this current is charging a capacitor. So, that way we can relate it to the circuit theory. So, the current input terms are the the current densities, whatever from different types of the plasma flux densities. So, already I said what are the different types we have discussed, and then you multiply it by the surface area of the either it can be the whole spacecraft or it can be a body of the spacecraft. Then you will get the what is the net current. Once you know this current, then you can use those that current to find out the potential built up. And because this constitute the forcing function of the equivalent circuit model of the spacecraft. So, it is just like a circuit. So, there is the current, and then if current is giving you the voltage, means you are charging a capacitor. So, as I already said, you have to derive this equivalent considering the geometry and the electrical parameters of the exposed surfaces. And once you develop this circuit model, so you can use it along with the circuit analysis program. So, there are the tool like the SPICE, you can use that one to determine the potential which is built up due to environmental fluxes, and you can predict the interior structural currents resulting from the surface discharges. So, all these things can be done when I am able to make the equivalent circuit of this spacecraft. So, this gives one of the example or a case study I am giving. So, this represents a spacecraft. This is the spacecraft bus or the structure, and then this is the solar cell, and these are the different antennas. There can be other subsystems also, but just just to show how it is done. So, what is done here, a capacitance matrix is formed. So, what you consider the different charge accumulation on different parts of the spacecraft, and then you write a that is called we call it say integral equation, where my charge is not known. So, what do we assume? We assume some known potential. So, if I consider known potential, then I can find, means what I mean to say that here the potential, it is a function of charge. So, what I can do, this is known, and this comes in fact in terms of integration. So, basically I can write it 1 by 4 pi epsilon 0, then integration. So, q I can write in terms of charge density, then so these are the this I am writing overall things. Detail. So, detail means when I write the potential for suppose one body, then I will consider what is the contribution by the other surfaces or other bodies. Like that we can form a set of equations, and those equation you can convert it into a matrix equation by using the it is called the method of moments. You can consider here the dielectric or the material properties, everything you can use it in this integral equation method, and you apply the boundary conditions, then those equations can be solved by a matrix methods known as method of moments. So, the method of moments, so this has been solved by the method of moments, and so this is the reference, this work is there in this paper. So, now how to find the temporal variation of this spacecraft body potential. So, this equation already we got it. Now, this has to be done numerically. This I nat will already we know how to find that I nat from the energy distribution, that is I nat will find it from the current density and the distribution functions. So, then the whole this equation need to be solved numerically. So, once you solve that equation, then what you need to use all those, what is the plasma environment, what is the plasma density, what is the temperature of the either electron species or the ion species. So, once you know all this figure should be known to you, what is the secondary emission yield, what is the backscattered emission yield, all those parameters, once you know it, then you can form these equations and then you can solve this equation, then you will get an the curve like. So, what does it show? That at time 0 the potential is 0, the spacecraft is not charged. Then since if I consider a spacecraft in plasma, it will be negatively charged, that already I explained. So, it will start negatively charging, and you see this charge, the potential is built up. So, means it is getting charged, and then this equilibrium condition comes. So, you can assume that after some 0.6 second it is getting constant saturated, or there is the equilibrium condition. At that condition the current will be 0. And if you see from this curve, this built up potential is something like that. If you exactly you can put from this curve, or it has come from the computer program. So, again this is from this paper, it was published in this paper, this work. Okay. So, this is all about in brief I described what is the physics, what is the probe theory, and starting from the plasma. Now, we will see what are the different types of the spacecraft charging. So, whatever we discussed till now, this is the surface charging, means the charges are on the surface of the. So, you can consider the spacecraft is a it is a conducting, a perfect conductor for the simulation. So, that means the charges will not enter to the spacecraft. So, that is called surface charging. Again, surface charging are two types, one is called the uniform charging or absolute charging. What does it mean uniform or absolute charging? That is, a uniformly charged spacecraft has only one potential, means this value is same everywhere. So, that is called as uniform charging or absolute charging. The other variation is differential charging. Now, what is differential charging? So, differential charging, the spacecraft is not a metallic structure, and it is neither a sphere or it is not symmetrical. Whatever we have seen in the earlier slide, it will have the different materials. It can have conducting materials, it can have insulating materials. So, since the different bodies have different the geometry, different material. So, there is the possibility that different parts can acquire different potential. Suppose two bodies are not electrically not connected, they are isolated. So, isolated bodies on the spacecraft connected by a dielectric can acquire different potential. So, if that is the case, when different parts of the spacecraft bodies acquire different potential, then it is called differential charging, and differential charging is very detrimental, because differential charging, if the voltage difference or the potential difference between two bodies, it exceeds the breakdown voltage of the dielectric, then there will be the discharge. And discharge means a lot of heat generation, then electromagnetic interference, so many effects that will be coming. What are the effects of the spacecraft charging? So, again this potential, what it depends on the surface properties of the as well as the environment. What is the environment? What is the energy of the charged particles? That everything depends. Means it is a function of the space weather. Mainly in the time of geomagnetic storm, there will be very highly energetic particles, especially in the high earth orbit, geostationary or geosynchronous orbit. There the spacecraft can have differential charging. The other type is called deep dielectric charging or the bulk charging. So, when the ambient electron or ions, they are very energetic, not in suppose it is a mega electron volt or even higher. This can happen during these solar energetic particle events. So, at those events, those charges can penetrate the spacecraft, the dielectric material or the circuit board, all those things deep into the dielectrics, and which are non-conductors. So, this is also we will discuss in the next slide. So, surface charging you can consider it is external, whereas the dielectric is the internal charging. So, now what is the deep dielectric charging, or it is also called the bulk charging, and even it is also called the internal charging. Internal charging. Okay. So, as I already said, this happens when very high energy electrons and ions, they penetrate the insulating materials of this spacecraft, leading to the accumulation of charge within these materials. So, this accumulation, this can generate internal electric field. So, whenever there is the charge, there will be electric field, and when this electric field, whatever the electric field, because of this the presence of the charged particles, when they exceed the dielectric strength or the breakdown voltage of the dielectric, then it will potentially result in the electrostatic discharge. Electrostatic discharge means it is no more insulator, but this it gets this it can forcefully make the dielectric conducting, means they are no more insulating. So, that happens only at very high voltages, and when those current passes through the dielectric, enormous heat is generated, because the dielectric will have very high resistance. So, I square R will be the law will be very high, and because of this high temperature, and it can result into the damage of the circuit component. So, it happens basically whenever the charged particles are having their energy is, or the temperature it exceeds mega electron volts. So, as I already said, this mega electron volt type of event may happen because of the solar energetic particle events, SEP. SEP again is related to the solar flare and the coronal mass ejection. This already we discussed a lot. So, you know what is that thing. So, those very high energetic particles, they interact with the dielectric materials, and they can deposit charge within the material. Okay. So, this deposition, they creates the electric field that causes charge redistribution until a steady state is achieved. And if the accumulated charge it surpasses the material's dielectric breakdown threshold, so the ESD will occur, and it will lead to a potential damage. So, through these cartoons just we can explain the thing. So, you just see this is the spacecraft the hull, means it can be some basically the spacecraft structure, like it can be CFRP structure, and inside that thing, or there will be not only the CFRP structure, then there will be thermal blankets and all other these protective coatings. So, and inside it is a it is a circuit. So, this is the circuit will have a conductive ground plane, then it will have a dielectric, and here all the circuit elements will be there. Now, what is happening this, because there is very high energy particles, they are entering to this skull, and it is getting impinged on the dielectric. So, what will happen, this will it will enter to the dielectric, and as already we said, then it will develop a potential, and then when it develops the potential, and that electric field or that field intensity when it crosses the breakdown, whatever the breakdown field or the breakdown voltage, when the potential, the accumulated potential will exceed the breakdown voltage, it will have a discharge inside the dielectric, giving rise to the deep dielectric discharge. Okay. So, now we will discuss what are the effects of the spacecraft charging. So, basically two types of effects. One is the damage to the onboard electronic instruments, that we will see what already how it does it, already we explained it. So, we will see it now in a more focused way, that is how it does that damage to onboard electron. The second is interference with scientific instruments. A charged spacecraft, if you put some instruments for some scientific observations, like knowing what is the ionospheric density or what is the magnetospheric, you want to measure what is the magnetic field and all those things, then it becomes challenging. I will come to that why it becomes challenging. So, the first type, what is called the damage to onboard electronic instruments. So, this is associated with the hostile space weather, mainly the geomagnetic storm. So, whenever energetic particles that interact with the spacecraft, then only the damage will occur, otherwise it is rare, it will not happen. But the second type, that is the scientific measurements, then even because spacecraft will be charged, whether it is low energy or high energy, it will be charged. So, the second type, that is the interference with the scientific, it will be always there, putting, and you have to design properly those instruments, considering that the spacecraft is not a neutral thing, it is a charged spacecraft. So, these are some of the to represent with how the ESD, that is electrostatic discharge, it damages the power system, that is the solar cell. So, this is from the onboard camera, this shows the flight solar cell damage by ESD. So, the satellite is the Eureka satellite, it is an ESA satellite. And this is the other one on this right hand side. This picture you shows this one is showing this a testing. Generally all these subsystems, whenever you are making, maybe for the first time, if does not have the space heritage, you need to do all sort of testing. So, it is during the testing it shows a ESD arcing. Okay. Now, let us see what is this damage to onboard electronic instruments. So, whenever there is a discharge, so discharge means it will create a lot of the noise, then the distortion, or it can damage the circuit. So, what is that? It affects the telemetry and the electronics on spacecraft. It can even the logical circuits and the computer chips, these are becoming smaller, and they are less power and they are very delicate. So, delicate electronics are very much susceptible to the charging anomalies, damage and the catastrophes. So, whatever these are all those currents, they are undesirable, because these are something like the noise. Okay. And until unless we are not able to harvest those things, these are the unwanted, this we cannot use it. And this, so what they do is they can conduct by through pinholes or via electromagnetic waves through the inadequate shielding, and those may cause disturbances. So, such disturbances can cause anomalies in the telemetry of the data and all those things. So, the telemetry is the very important subsystem, telemetry, then tracking and telecommand, and this if this system fails, so in that case it will be difficult to control the satellite. Okay. So, this point, whatever this, if the neighboring surfaces are at very different potentials, so means it is a case of a differential charging. So, this is a case of a differential charging. So, there is a tendency for a sudden discharge to occur, and the discharge it can be small, large, frequent, or it may be depending on what is the type of the space weather, but the discharge is the electrostatic discharge is not a desirable phenomena. It creates many other problems that already I told you. And so, this size of the whatever is mentioned here, the size of the discharge depends on the amount of charge built up in the electrostatic capacitances. Means spacecraft we are assuming it is like a capacitor, and the amount of the the neutral materials such as gas which may be ionized when a discharge is initiated. So, all these things it affects the discharge and the subsequent effect on the spacecraft's subsystems. So, an avalanche ionization can lead to a large current and differential charging, this already we said, and if the discharge is small, it can be simply a spark generating electromagnetic waves, and even that it can be a small discharge, but whatever the electromagnetic waves they generate, this will give rise to the electromagnetic interference or EMI. And whenever a large discharge, it may cause damage to electronics, which in turn affect the operations, navigation, or even the survivability of this spacecraft. So, why the discharge it is called electrostatic discharge, because here this phenomena of that is the charging, it is very slow. So, slow means this the built up is very slow. So, the magnetic field associated magnetic field is not involved. So, you can consider it say, since it is very slow process, it is that is why it is electrostatic. Had it been very fast, then there would have been the magnetic field associated with. So, this is the reason it is called the electrostatic discharge. Okay. So, discharge always it is not harmful, sometimes it is done deliberately also. We will see that how it is done when we will study the mitigation. Sometimes it is the reducing the charges is also called the discharges. So, we will see that as that comes one of the mitigation technique to the plasma contactor, we will see that. So, now we said about the surface charging, but if the electrons and ions are of higher energies, suppose if it is mega electron volt or higher, so they will be able to penetrate, pass through and deposit inside the material. So, this high energy electrons, they may stay inside the non-conductor, that is the dielectrics, for long time and giving rise to the bulk charging, and that bulk charging will result into the damage of the circuit. And if the field is high enough, it may be sufficient to cause a local dielectric breakdown. And whenever a local breakdown occurs, the ionization channels develops extremely rapidly inside the dielectric, allowing the currents to flow, and this in turn generate the more ionization and heat. So, as a result, the internal instruments may be damaged, and the densities of high energy, whether it is mega electron volt or higher, and the electrons and ions space, they are generally they are low, but since it is very high energetic, so that is why they can enter to this spacecraft. Okay. So, internal damage events are rare, however, when they occur, they may in extreme cases it can cause the loss of the spacecraft. Now, we will see the interference with the scientific instruments. So, there are various types of probes are used, like Langmuir probe, or it can be magnetometer. So, these are for the the scientific measurements of the space plasma properties, plasma density, what is the the mean energy, plasma distribution function, all these things you need to in situ measurements by using different types of the probes. But if the spacecraft is charged, then those the measurements will be influenced, because spacecraft can be non-neutral, like in the ionosphere. The ionosphere, the density is or the energy is very low. So, if you want to measure very low voltages, that is the electron volt or the energy, then if it is the probe is inside the sheath or in the non-neutral region, then you will get very misleading result. You will not get the actual the properties of the plasma environment. So, these are the interference with the scientific instruments. So, with this I will end here, and in the next session we will discuss the different mitigation techniques, what are the design guidelines. Thank you very much.